Maybe, I'm not, I'm just going. So we'll go ahead and start. So what we did last time is we just sort of had introductions, got started. As I said, we're looking in this class at two types of data, very broadly speaking. Three-dimensional data, which is seismic reflection data. Bill Keach is an expert in this, among other things, and he gave you a description of that data, showed you some examples from the ADM site in Decatur, Illinois. We'll be looking at other sites, but just to repeat, the ADM Decatur site is probably the premier site in the United States for carbon dioxide, speaking of carbon dioxide, sequestration, so carbon capture and storage. So it's a very high profile place. It's just not some random data set we picked out. It's actually associated with probably about $1 million of funding within this university over the past several years. So it's an interesting data set in that sense. It also has very well developed microseismicity, which we'll talk about in due course. The second type of data category is well log data, which is sort of one-dimensional. It's beneath the point. So depending on how you define 1D versus 2D, it's basically looking at properties at a point in the subsurface, okay, along a line of your wellbore. So we talked about, to get started, we talked about the divisions of your well log data suite. So what would be on your left? What type of data, well log data? We have like 3 tracks, if you think about a display. And part of a display here, just to refresh your memory. So we had 3 tracks. What would be on your leftmost track? What type? What information? Are you getting temperature, pressure? What are you getting?
I think you're getting density.
Well, you're getting lithology. We define lithology as rock type. Yeah. Okay, so it's not really density. Well, you could infer density from it, but actually you get density from another part of the log, which we'll talk about later. But you get your rock information, so to speak, information about the matrix. And there's different types of lithology or correlation logs. Correlation because you use those logs to say, well, we're in the sand A here, the sand A here, the sand A here at different places within your oil field or reservoir, or in this particular case, our injection site. So that's your correlation track and your lithology track on the left. Lots of different types of logs. We talked in a little bit of detail about the gamma ray log, which is passive active. Do you remember those terms? So which would it be? Passive, it's listening, well, not exactly listening, but recording the what?
The radiation emitted from.
Right, and what type of radiation? Lots of type of radiation on the gamma ray, as the name says, okay? So it's a very useful log. It's probably the most nervous log in your lit track, meaning that it has the greatest precision, also greatest accuracy. So it's the most important to define bed boundaries. And given the context, if you understand the context and you have enough assumptions that you understand, you can use it to define what versus what. Kind of shown here. What versus what?
Shale versus sandstone.
Shale versus sandstone, or more generally speaking, think like an engineer. As engineers, reservoir versus seal. Although you have to be careful. Remember I said given the context. If you understand the context, that'll work. In this particular case, this is where we left off last time, looking at aquifer versus not aquifer. Not an oil company example, but a civil engineering example. How would you be more careful? What versus what? For the gamma ray log. Think about what gamma ray is measuring. What would you say that you're always right? Now, if you say reservoir versus not reservoir, maybe you'll be right if you're in the proper context, like Gulf of Mexico, which we're not exactly here. So you may be right in some cases. What would you say what versus what with the gamma ray log? You'll always be right.
Clean versus not clean.
Yeah, clean. So clean meaning?
High radiation, low radiation.
Yeah, so geologists like to use the word clean. Doesn't have any oral implications. It just means is it free of potassium, thorium, or uranium? That if it is, then it's clean. It's clean of that, right? Now, it doesn't mean that it's reservoir, because it could be solid glass, right? And what do geologists call solid glass if it's a rock type? Fused glass. Quartzite, right? Now, if you haven't had geology classes, that doesn't mean anything, but you probably heard the word quartz, silicon dioxide in crystal form. You often have that as a rock type, where it's solid quartz. It's actually a metamorphic rock, but it's got no porosity. Okay, So it's basically like fused glass. So that would be clean. So where would that be on this example here? If you had fused quartz, no porosity, tell me where to stop.
There you go.
Right here, right? That's what it would look like because it has low gamma radiation. Remember, these units are kind of funky units. API, American Petroleum Institute, gamma ray units. They actually mean something, but we won't go into that. They're based on a calibration back at some mud pit in Houston. Okay, we'll just leave it at that. Okay, so this would be, so the way to always be right is you'd say that, well, if you have a cake all the way to the left, well, always be right is clean, meaning it has no potassium or thorium or uranium, anything that produces gamma radiation. Okay, if it's dirty, to use the term sort of opposite of clean, well, dirty meaning that it's doesn't need a bath. It means that it does have potassium in it. Okay. So what type of minerals or rocks would you have high potassium? Shales. Or if you're talking about minerals, clays. I'm not an expert on clays, so if I say clay, we all understand what we're talking about, right? So snectite, montmorillonite, illite, those are terms that an engineer might encounter if you're worried about a building site, what clays well versus not. So we understand what clays mean. Have a high degree, usually of potassium. So this would be where you might expect to find clays, and over here to the left, and kick to the left, where your reservoir is, if you have the right conditions. But you can always say it's clean to be right. Does that make sense? So the way to deal with logs is just don't say, oh, that's a sandstone, or that looks like a limestone, or that's kind of a shale, or maybe that's a dolomite, or run through your list of possibilities and try to attach that. You'll likely be wrong, unless you're just working in the same place and you know those 3 or 4 or 2 always work. To always be right, you think about what the logs are actually measuring. That's why it's kind of important to sort of drag it on a little bit. So this is where we left off before. Remember how to do this. There we go. So if they drew a line here and just said everything to the left is an aquifer or reservoir in this particular case, or everything to the right is what? Is not. Okay, so good reservoir versus poor reservoir. And again, if this were a oil company setting, and as we talked about before, if this line moves to the right for your cutoff, and you sort of color in or dot in or have your program shade in more and more as reservoir, that means the price of oil is doing what? Going up because you're going for the last drop. So who knows? Somebody, this class we were just in, Bob Lindsay, petroleum geologist, very successful, said he was in a setting once where they calculated that, well, for this particular prospect development, they had in mind the price of oil had to be $2,000 a barrel. So if you had $2,000 a barrel of oil, well, maybe this little thing would be worth pursuing, right? But I remember I was working for Shell Oil Company one time, late 80s, the price of oil was $12 a barrel. Well, maybe this cutoff is like over here. Nothing's good, okay? Okay, so that's where we left off last time. So that's how they would interpret this. Okay, so here's kind of a test, right? So just to show you how one of the points that we made is actually true, that gamma ray logs can be very successful, useful for constraining, not determining, but constraining your interpretation of lithology. But it doesn't conclusively answer the lithology question. There was the fine print in one of those slides. Well, this is going to prove that. So here's a gamma ray log. Just ignore this one for now. Here's a gamma ray log, same kind of units, 0 to 100 API. Okay, so similar types of units, and there's not a scale here yet, but it's got depth on this axis. So what do you think this is? So the first thing you say, it has, it's clean or dirty. So it has high radioactivity, so it's got to be dirty, meaning maybe it's got some potassium, thorium, uranium. We'll just say potassium, that's the most common one, okay? So being very careful of that. So you might say it's what? What type of rock type?
Maybe a shell.
A shell. Be your knee-jerk reaction. Now, if you look very carefully on the slide, it's got the word Iran in it. Okay, so they've got, if you're a geologist familiar with the Middle East, you think, oh, the geology there is very different from the Gulf of Mexico, where a lot of our examples are from. Okay, so to be careful, you would say it's dirty, it's got high potassium, could be uranium or thorium. It could be a shale, but at least we know it's dirty. Okay, what about this one? What's that?
Something in the reservoir, what's in there?
Okay, so to always be right, you say it has less amounts of potassium. Don't say no, because we don't, it's not zero, but it's pretty darn close to it. In fact, maybe it is actually zero. It's nice and blocky, okay? So you kind of get an idea, dirty-ish, clean, dirty, kind of clean, dirty, and so forth, all right? So, as far as what type of rocks, well, it actually could be infinite. You take all the rocks out there, well, it's not infinite, but a very large number, okay? But here's a scale showing the different interpretations based on actual core data, and this is the key. So let's look back at this one. So when geologists draw horizontal lines like this to denote some type of rock type, that's supposed to make you think shale immediately, okay? Now, if you look over here, it says marl. What's a marl? Some geologists help me out. What's a marl? M-A-R-L.
Dirty limestone.
Yeah, so limestone's got some clay or a clay, it's a clay-rich limestone or a calcareous shale. So geology is very messy, right? That's why, you know, you can't just say, well, here's my 3 possibilities, or my 10, or 100, okay? There's always a transitional phase. So a marl is something that you call it a calcareous shale or a dirty limestone, okay? Lots of cases of that. So that's what you're seeing here. The clay is giving you a hint that you've got some, the clay is actually producing some of your potassium signature that's causing the gamma ray to kick to the right, So what about this one? So we kind of got that one right. Shale-ish, okay? But if you said reservoir for this, well, how'd you do it? It's salt. Salt meaning sodium chloride, right? It's like halite. So do you understand the signature here? Salt is a very common component in the rock column. If you ever go to work, well, here in this part of the world, which may not be so likely, but certainly if you work in the Gulf of Mexico, you're going to be dealing with salt all the time. I worked a number of years in the Gulf of Mexico, worked for an oil company, and salt was one of our big rock types. Makes a nice seal, but how does it appear in a gamma ray log? Very clean. So you got to be careful. Your knee-jerk reaction may be to call that, well, hey, shale, reservoir, reservoir, okay? But it's actually not a reservoir at all. In fact, this would make a better reservoir. This has potential to have oil in it, especially unconventionally speaking, but you're not going to find any oil in salt, okay? And then what are some of our, just to make it even more interesting, we got some other rock types here. This one is colored differently. Geologists like to color things. So in this case, it's hard to read, but it's anhydrite. Now somebody help me out. What's anhydrite? Very common mineral and rock.
It's like gypsum but without water.
Yeah, so you know what gypsum is like, you know, stuff you use for drywall. You know, so what's the chemical formula for gypsum? Or just tell me what it is.
CaSO4.
Yeah, so calcium sulfate with water. Anhydrite, meaning no water, anhydrite. It's basically gypsum without the water, as Alex said here. A very common mineral type, often associated with salt, for reasons that we don't need to go into right now. But you also have this here as well. So you have, this just shows kind of a cautionary tale from a real live example, just didn't make it up, it's not from Mars or something, where you have something that looks like a reservoir, but it's not a reservoir. Okay? So you have to be careful with how you interpret these logs. You don't just pick from 3 possibilities that you have in mind. You actually think about what is the log actually measuring, and then you interpret from that. Okay. Now, from our site in Illinois, there's not such a diversity of rock types as we might show in some of these slides, but who knows, it might come up. And we'll actually look at some examples like right now. I've showed this slide before, so Alex has seen this already. But this is a log from our carbon sequestration site. So this is from Decatur, Illinois. It's not actually in Chicago. This is just shown for scale. Sears Tower, I used to go to school right there. It always was a miracle that I got out safely. Used to be called the Sears Tower, but just to give you an idea of height, so the antenna is 1730 feet above the ground surface. Our injection zone is right about here. Okay, so this is our porous injection zone, just to give you an idea of scale. So 600 feet thick. That's a lot of reservoir. Okay, now this is porosity. We haven't talked about porosity. We will a little bit, but suffice it to say that high porosity is to the left. You kind of remember this from the pattern recognition. If you think back, high porosity to the left. It kind of goes with reservoirs sometimes to the left. So if they're both going left, then you start to have nice feelings, right? So I have a nice feeling about this because my porosity here, I don't know what the maximum scale is. Can't quite see it on this slide, but we'll have another one. Is showing fairly high. So that's good for injection, right? You can inject into no porosity. Now, this is gamma ray. Forget about the middle one here. Here's gamma ray. It's the leftmost lift log. Now, what's interesting about the gamma ray? Notice they've done something similar to the ARC, for example, a couple slides ago. They've just drawn an arbitrary line and said, well, just to catch your eye, I'm going to mark in red everything to the left of a line within the gamma ray. That could be possible reservoir. See what that's a typical thing to do. They've done it with both. So where are going to be the best places where both are red, right? So maybe like, oh, right a little bit there, but maybe right there. They're both red. Get the idea? Pattern recognition is supposed to help. If it's not helping, let me know. I'll explain it. But here's your injection zone. This is where they actually chose. Now, why doesn't quite make sense? Why would they choose this? This is basement. This is top of Precambrian basement. There's actually a huge unconformity. Right here, there's about, just to give you context, there's about 1 billion years of time missing, meaning sediments missing. 1 billion years. That's a lot, right? That's more than the entire Earth history for the Paleozoic. Okay. So what do you notice? What's not quite right? What have they perhaps done wrong? Now, you know they haven't done anything wrong, but what do you not see in the gamma ray?
It's not giving you a lot.
Yeah, you don't see that, it's not redded in, okay? That's a word. So let me just have a blow up of that. So the question I'm asking, why is the gamma ray high, meaning that it's looking dirty, in the high porosity zone for carbon capture and storage? Or just to blow that up, that's the area we're looking at. There's a slide, a little bit easier to see now. This is our injection zone. 10% porosity is right here, just for reference. Here's 30%, just for scale. And then look at the gamma ray. It doesn't look very great compared to other places. In fact, other places look much better that are actually low porosity. So how would you actually see what the problem is? If you were you might find yourself in this position. You're giving a talk to management. I had to do this, right? And you show a log, and you're talking about, you're reviewing things. It's all kind of been decided, perhaps, but you don't know everything about it. Saying, well, this is our injection zone here, and you're kind of lecturing, kind of like I am right now. And it's got high porosity, and this is just showing our gamma ray. And the boss says, wait. And the boss doesn't know everything, right? He says, well, that doesn't make any sense, because that's showing it looks like a shale. Why are you injecting within what looks like a shaly zone? What do you do? How do you explain that? Well, you might start at the beginning, as I said. It's like, well, the boss says, well, that's got to be a shale. And you say, well, let's back up a little bit. It's got high gamma radiation, relatively speaking. That doesn't mean it's a shale, right? This means it's got high gamma radiation, which means that it has what? High potassium. Does that mean it's a shale? No. So the geologists, I've shown this to Alex, you've already seen this. You have to be quiet for a minute. This is actually a piece of the rock. Notice I'll turn on the light. You just pass it around the light a little bit. That's not from the core, but that's from an outcrop that is basically the same thing. Okay, because it comes up to the, and this is those So that's the injection. Is that a shale? Geologist should help me out. It's not a shale. Okay, so what color? I mean, you can actually stand way back and see that it's got some color to it. It's blushing a little bit, right?
Is it some kind of sandstone?
It's a sandstone, generally speaking, but it's got some other stuff in there. There's some pink grains. It's getting that pink sort of cast to it. Now, if you haven't had a geology class, you're off the hook. But where do you think I'm going with all of this? It's not a shale, but it might look like a shale if you don't know any better. It's got something in there. It's got potassium. Now, it's not quartz, because quartz is what? Silicon dioxide. So there must be some other mineral out there that's high in potassium. Maybe it's pink. Yeah, something called feldspar, right? So, or orthoclase, lots of different types of names, right? But it typically has a pink color to it. So, and the rock type is called what? Some of you know this. What's the rock type? When you have a sandstone with lots of feldspar in it, and I don't want to get into depositional environment discussion too much, because it's not that, we're not ready for that. But what type of rock type is it? It's called an arco. So that's a funny name. But if you've ever been out, west of Denver, they call it Red Rocks Park or something. Anybody ever been there? There's a little park, lots of parks to go to. But the west side of Denver, it's a place where they call it Red Rocks Park or something like that. There's a famous Arcos. That's not what that is, although it's actually similar to it. Where you have the sandstone, it's got this nice pink tint to it. It's an Arcos. So what's the moral of the story is that just because you've memorized 3 or 4 rock types and their signatures on logs doesn't mean that it's going to be correct. You could have the slightly weird rock, and that's not really a weird rock, but it's a little bit weird. Okay. Do you see what the point I've made is? So again, the moral of the story, think about what the log is measuring rather than saying, well, that's got to be a sandstone or a shale or limestone, and if it's not, then I'm completely out of ideas. All right. Okay, so let's keep going. Now, this is something I talked about in another class, so again, sorry if it's a little bit overlap. But what geologists use these logs for, other than just trying to say, well, where's high porosity, where's the zones complete, to try to reconstruct what's called a sedimentary environment. Was it a lake? Was it a beach? An ocean? Was it a lagoon? Was it deep water? Right? Was it a delta? Was it a braided stream? On and on and on. Okay, called sedimentary environments, and you can do that from the log patterns because if you do believe that you're looking at a shale versus sand environment, like in the Gulf of Mexico, a lot of logs in the Gulf of Mexico. Okay, so we could be forgiven for saying the Gulf of Mexico is basically the entire story because there's lots of data from the Gulf of Mexico. If that's where you're at, then you could be forgiven for saying, well, it's basically shale or sandstone. Those are my 2 possibilities, right? And shale is fine grained or coarse grained.
Yeah.
Fine grained, it's got high potassium, so it's fine grained, it's got high potassium. But what about environment of deposition? Very simplest way you could think about that is it deep water or is it shallow water?
Deep water.
So it's deep water. So it's low energy. If you're down in the water off the Gulf of Mexico and you're at 3,000 feet depth, hope you hold your breath, but there's not much energy down there, right, except for occasional turbidite flows or something. It's very low energy, very fine grained stuff that's just settling down very slowly. All your coarse grained stuff has already been dumped out of the water because it slows down as it's coming from the source area. And as the water energy slows down or drops, then it drops its load, so to speak, of sediment. Okay, so you can think of shale and low energy and fine grain and deep water as 4 things that go together. Make sense? So fine grain, so shale, fine grain, so very small grains, deep water, low energy. Okay. Now you can actually find that kind of signature on a gamma ray log or an SP log. These are actually SP log examples, but it applies equally for gamma ray logs. And what geologists will do is use that pattern of shale versus sand, because sand would be shallow water, just the opposite. Shallow water, high energy, coarse grained, low amount of potassium. They use those relationships to try to understand water depths. So here's just an example log showing regression, meaning the regression of the sea. So it seas transgress and regress. So if I put my finger right here, better careful, there's something strange on the screen. If I put my finger right there, what's the water depth there? Or well, let's go back. What's the potassium level there? This is gamma ray log, high potassium here, dirty, low to the left, right? So this would be high potassium. If it's Gulf of Mexico, then it's a shale. We call this a shale baseline, in fact, because I keep my finger in the same place, all right? So what's the water depth? It's deep, it's low energy, it's high potassium, okay, and it's shale, fine grained, right? It's all those things. Now, what do these bumps here represent? What about right there? So it's shallower water, right? It's coarser grained, so it's more sandy, right? So that means it's closer to the shore, so it's shallower water, it's higher energy, it's lower potassium. That's the one thing that's always true, right? It's lower potassium. So you can actually construct water depth if you make a bunch of assumptions that you're in a certain kind of environment, right? Like Gulf of Mexico, you would say that's deep water, shallow, deep, shallow, deep, shallow. Does that make sense? So this is like a sea level curve. But it's sea level curve based on the interpretation of coarse grain versus fine grain. So are you still with me on this? Kind of a lot of things you got to connect together. So if it's too much, draw a picture, think about it some more, okay? So which way is the sea moving as I go from older time to newer time? It's like a stratigraphic column, so like a rock outcrop. So this is older rocks, this is younger rocks on top, obviously, in this particular case, okay? So what's happening with the sea? I'm right there, the sea level is, it's got to be high sea level because I'm in deep water right here. But up here, you know, I'm standing in one place. So I'm standing here, one place, and it's deep water. But by the time geologic time has moved on to this point, I'm in shallow water. So what's happened? The sea has moved out, right? So that's a regression. So, and then on, you can make other types of interpretations. Just the opposite is a transgression, the sea moving up over you. Okay, so in that case, you're going from, you have nice beachfront property here, okay, and you're underwater here, okay, because the sea has transgressed over you. Sea level has risen, okay. Now, rising sea level and transgression aren't necessarily the same thing, but for these purposes, we can equate them. So, you could spend a whole class, all the different types of environments you could reconstruct. Of course, you could do this in multiple dimensions. But I just want you to be aware that this is something you can do with the logs that you have. And actually, that has been done with the logs that you have, along with the seismic data, to infer deposition environments. We talked a little bit about that last time. I'll say a little bit more now, right? So here's an example of a what? This is a picture from Britain. It's not exactly an oil province. Well, it is, but not right here. What is this thing? What would you call it? Barrier Island, right? So like Long Island, except it's a lot cleaner, okay? So this is a barrier island. This is your lagoon. This is the mainland. Deep water is out here somewhere. So if I had a gamma ray log that represented this environment, what would it look like? Right, so you'd have something like, I don't know if these work. So if this is my gamma ray log, I'm going from, say, 0 to 100 API units. Well, if I had something that looks like this, well, this is my what? Shale baseline. Shale baseline. Given my assumption being correct that I'm working in that type of environment, right? So shale baseline. And this would be what? Well, this could be that, right? Because this represents low potassium. This is high potassium. Or clay rich or sand rich. Making the assumption that I'm working in a so-called clastic environment. Okay. So, what about this? This is more familiar. Gulf of Mexico. Where's New Orleans? New Orleans is on here somewhere, right? So I used to live right about there. Right about there. Okay? Not that that's important. But not messed up. Okay. So, where would you expect the highest? This is just a blow up, kind of a perspective view. Okay, here's your channel, right? Somewhere in the delta. Where would you expect your gamma ray signature to look like this on this slide? So out here, deep water, no. Maybe right here where you have high energy. Because this is low energy, so this could be clay, muck, gumbo, whatever your favorite word is, okay? Shaly stuff. Whereas here, it's in a channel. So you have the waters coming through pretty fast, right? So here you have coarse grained stuff. So if this were frozen in time, that kind of happens, right? See, it moves over and buries everything. But if you froze this in time and made it all into rock, and then somebody drilled holes through it and logged it, this, the sandy part, would typically look like that. Or vice versa, okay? So what's then done is to do all this over and over again with lots of different wells and different locations, and then come up with an interpretation. So this is supposed to be a delta system. We can spend a lot of time on this, but I won't, just to get through it. So here's our channel here. This represents our deltas, and this is the Mississippi River. Here's your delta. The letters represent different environments. So let's say we take a cross section like this down perpendicular through the delta. Okay, so it's down through the river. So if it's coming through the river, well, here's the channel. I don't know if you see that, which is A channel, right? A channel, okay? And then as it gets into deep water all the way to E, E is off the edge of the delta. You're in very deep water. Low energy environment dominated by clays. So you have lots of potassium, right? Here you have lots of sandy stuff. So sand meaning quartz, okay? So then what would a well log look like if you drilled it right through here? In this in the map view, or this is a cross-section view. I hope you get the geometry. Cross-section view. How do I? Okay, I guess I kind of got this right. So it senses my fingers. Okay, great. I'm alive again. Okay. So this is what your well log would look like, right? You're right within the channel. Now, what would your well log look like if you were, say, having a cross-section coming through here? The black line, this represents an interpretation going through the cross-section. It's kind of a bar of sand that's developed right off the edge of your river, but it's kind of far out to sea. So it's again like a barrier island, but it's just further out. So it's sometimes called a distributary mouth bar, or distal, sounding fancy, distal meaning far away, bar of sand. You might look like this. You have intervals of sand separated by long intervals of shale. You see what's happened is that you just have something that's developed offshore, but it's ephemeral, and then it's buried, and then you have more fine grained stuff, and the sea level changes, it redresses, and then it gets to be higher energy, going back and forth, or something like this. This is called the Chandelier Islands off of New Orleans. I don't know if they're there anymore. I've actually been there, but it's like a long time ago by helicopter. So New Orleans is way back there. This is actually between the distributary mouth bar and the delta. See, this is all kind of shallow water here. If you drilled through this, what would you expect? Well, you'd expect to get something like that, right? So anyhow, this is probably made the point is that you can use your gamma ray curves, also SP, but we're talking about gamma ray curves, to get an idea about grain size. And if you have grain size in deposition environment, but only if you're working in something like plastic rocks. Plastic meaning rocks that developed from erosion and redeposition as opposed to, say, chemical precipitation, right, which would be limestones. So then you can get diagrams like this. This is what I just drew on the board. This could be a channel. If you have a pattern like this, geologists help me out. What would this represent? So what's happening to the grain size as I go up? can't touch the street. It's getting finer. So we call this fining upward sequence. What about this one? It's getting coarser as you go upward, or that would represent a regression of the seas. Okay. And then this represents just deep water shale, and this is just sort of oscillating back and forth, right? So, given the right assumptions, you could actually read these curves, given the right assumptions, you say that very carefully, as showing water depth and grain size. Okay, so geologists use that then to reconstruct depositional environments. This is just some examples. Again, coarsening upward. You have shale here, but you have more quartz. Dirty here, cleaner as you go up the section, right? So that corresponds to different types of sea level rise and fall. Okay, so I'm not going to dwell on this, but to show you where you can go if you get really into this. I know this is going to recommend that you do. I guess I shouldn't say that. I'm a geophysicist, so I don't get too much into this type of work. But you can eventually reconstruct in a cross-section view what your environment or deposition look like. Now, this is not merely academic, right? Because this is of interest to petroleum engineers, petroleum geologists, geophysicists, and their investors, obviously. Because do you see anything interesting about this? This is a cross-section. This represents sandy deposits, or excuse me, this is shaly deposits. These are sandy, so sand, shale, sand, shale. What archetypal response, if you're a petroleum person, do you have? It's a trap, right? It's a trap for oil, or stratigraphic trap. So these kind of sections are not merely just for power games or bored academics. People make millions and millions of dollars doing this, obviously, okay? And they're all based on these well logs, which if you give them the right interpretational constraints, you can read as water depth, deposition, and grain size, okay? So let's look at one of our own examples. I've shown this before. This might have forgotten, but this is a map, a contour map of depth below sea level, depth below datum of our study area in Illinois. So here's a positive feature. So the reds, make sure you're comfortable with the units. So this is looking shallow. I think I got this label. This is looking shallow, that's looking deep. So positive, sticking up, something that's bowl-shaped or trough-shaped, looking down. And it got the picture. Now, what we want to be able to do eventually is, well, how does the depositional environment affect the compartmentalization of the CO2 injection? Because the CO2 is not going into a rock that's all just shale, or all just sandstone, or all just one thing or another. It's these environments of deposition that are always changing in 3 dimensions that cause compartmentalization of your reservoir. And compartmentalization is something you can actually capture in a model. An engineer can do that to predict the efficiency of flow. A big deal with this whole project that people have agonized over, I'm glad I'm not part of it, I mean, that's not my particular role, is to worry about, well, in 20 years, where is the gas going to go? Is it going to stop? What's going to stop it? Is it going to slow down? Is it going to end up in Peoria? Is it going to come back up to the surface? That's bad. And to be a little bit cynical, they show these diagrams showing, well, in the year 2070, the gas will be here. We're all thinking, oh, we'll be dead by then, so we don't care, right? Our funding will be gone and be somebody else in trouble. But how do you actually answer that question? How do you actually start to think about it? By depositional environments, right? What's actually going to make the reservoir all of a sudden shaly and stop the flow? Well, that's a depositional environment question. So to answer that, I showed this before, there's been a lot of trying to relate your site in Illinois to a site that couldn't be more different, right? In this case, Death Valley, which is a big rift basin. You all know where Death Valley is. And the idea being that, well, some of these depositional environments that you have out here in Death Valley are similar to those that you used to have beneath the site in Illinois. Of course, that is about 500 million years ago. Okay, so for example, these buried hills could represent something like this. So one interpretation is that this is a buried hill, and the buried hill, such as shown here, is flanked by what? What do you have on the side of the mountains in Death Valley? You ever been to, or the Basin Range in general? You start driving here towards Reno, where you have these things called alluvial fans. This is where your water comes from. Okay, Alluvial fans hold a huge amount of water. Here in Provo, now we get a lot of water from our reservoirs, right? But when the pioneers first came here, there weren't no reservoirs. Brigham Young came over the mountains. He didn't pass by Strawberry Reservoir, Deer Creek Reservoir. Where did the water come from? It came from alluvial fans. That's why Utah is so densely populated here as opposed to out in Dugway Proving Grounds, for example. Okay? Dugway Proving Grounds is there because there's no other reason to be there because there's no water. There are no alluvial, well, there are some alluvial fans, but not like you have here. Okay. So this is an attempt to reconstruct, at least in your mind, what the depositional environment would have been like for your reservoir in which you're injecting, and that's a piece of it right there in Illinois. If you draw a block diagram, you might come up with something like this. This is for some other place, obviously, but it's perhaps similar. You have alluvial fans, you got deltaic deposits, small deltas. You have these so-called braided streams where you go from coarse to fine, coarse to fine. If you do any field work or just go hiking in some of these places, you'll cross some place where, like, well, there's this place with big boulders, must have been a huge amount of water coming through here. And other places where it's very fine grained or just clay, mud. You can see that any of these kind of types of environments you can go, like anybody been to Wendover, probably been through Wendover on your way to Reno, whatever, or on the way back from Reno. You cross these basin range types of settings. Well, you can see all of these things here in Utah and Nevada. Death Valley is just a very good environment to do that. But the point is that this is all reconstructed based on well logs and based on your gamma ray log. Okay. So I think that's it for gamma ray logs. Again, SP logs are also in there. They're completely different, but they're used for a similar purpose of reconstructing your lithology and then correlating from well to well. So that's it for the left track. How are we doing? It's supposed to end at 4:45, right? So you'll get up and leave, right? That's my signal to stop. Okay? I won't be offended, I promise. Okay? So that's our leftmost tracks. What is our middle track? Is this one, right? Electrical resistivity. Now what's the deal with that? Why do we care about electrical resistivity?
Can you not tell us if it's a fluid or not, or if it contains fluid?
Yeah, it tells us something about the fluids because most rocks don't have a lot of good conductivity. So if I pass that rock around again and ask you to point to something that's going to conduct electricity, there's not much in there that's going to do that. It's going to make a pretty good insulator. You would like to have that rock separating you and electrical current. All right, it's close, sort of close to glass. All right, and that's true of a lot of rocks. Clays being the one exception. Okay, but a lot of rocks are actually insulators. The matrix, the solid part. But what about the fluids? Fluids, what? I'm doing a lot of talking. I think I'm probably violating some pedagogical rule by talking too much. So you can get me out of it by participating more, but or getting a word in edgewise. So what's the deal with fluids and electrical resistivity?
Well, I think their salinity also affects it a great deal, right?
Yeah. So so when you drill a hole in the ground, your water is going to be fresh, probably. Well, in a lot of places, fresh water. That's the scary thing. Most of the water in the earth is salty, almost all of it. Very, very, very small amounts is actually drinkable. Okay, but that fresh water is going to have lower or higher conductivity, higher resistivity compared to salt water, a little bit. Both will electrocute you, right, if you put a wire into a pot of it and stand in it. But salt water have a lower resistivity. And of course, what's the other fluid we're interested in is oil, right? And so what's the deal with oil? It doesn't conduct electricity so well, right? So all of your variation, you'd like to think in fluid characteristics, particularly those characteristics that you're interested in, oil versus non-oil, are going to be captured by your electrical resistivity. So your middle track resistivity is not so much about your matrix, except unless it's clay, but it's about your fluid. Okay, so let's just talk about, this is review, I'm sure everybody knows this infinitely. Electrical resistivity, so resistivity can be defined as what? Resistance times the area divided by the length. So if you think about a wire, for example, okay, a simple object, where A is cross-sectional area, L is the length. So again, you think about a wire. Anybody who grew up on a farm and had hot wire, electrified fence, you always call it a hot wire. You say electrified fence, they think you're putting on airs, okay? You don't touch it, right? Because the current that travels through it is going to be related to the cross-sectional area and the length, okay? But resistivity, ohm meters, right? Ohms is a unit of resistance, small r versus big R. Resistivity is an intrinsic property of the medium. Now, what do I say what do I mean when I say intrinsic? Intrinsic property of the medium. It's built into it. It's intensive or intrinsic. Okay, it's a character like density, right? If I pick up a substance, quartz has particular density, 2.65 grams per milliliter. You can measure it. It's consistent, right? It's just related to the chemical structure, all right? But resistance actually depends on geometry, the length of something, how wide it is, how long it is, okay? So geologists use well logs to measure resistivity, not resistance. Very important, okay? Because if you're measuring, well, actually resistance is a measurement that's made, but what pops out is resistivity, or conductivity, just resistivity upside down. So it's important to understand that because your units are going to be ohm meters. It's one of the few cases where you actually have metric units in well logs in the United States. Okay, because otherwise it's feet and so forth. Okay, one of the few cases where you actually have metric units. So resistivity is what you're actually measuring with your resistivity logs, obviously in its ohm meters. Okay, so what is it? Intrinsic property, medium. It's just how a current is impeded by the medium. Just to measure, well, it's actually ohm. If you look at your units, your expression for little r, well, it's actually ohm times meter squared divided by meter. This is area, this is length, right? And you divide the two, you get ohm meter, okay? So our formation resistivity. Now, just a little bit about symbolism. The T stands for true. The true resistivity. Now, what does that mean? Is there false resistivity? What am I trying to signal here by breaking out different types of resistivity? Versions of resistivity. How do you have different resistivities within rocks that are penetrated by a borehole? I thought you just said it was an intrinsic property of the medium. Well, it is, but the medium has been changed. When you drill through it and you have mud that's doing what? It's invading, and so that mud has its own resistivity that you know something about because you designed it at the surface, and you can check that. It's actually written on your log header. So many ohm meters as a function of temperature. So T must be what? T is for true. So what does that mean?
Incorrected.
It's been corrected, but where is it within your overall scheme? If this is my borehole, it's the air picture, right? This is my borehole and I have rocks. Is the rocks right next to the borehole? It's beyond the zone of invasion. So it's the uninvaded zone.
How do they correct for mud resistivity? Because aren't they constantly changing the mix of the mud to account for pressure and whatever the
Yeah. So why would you change the mud?
make it heavier so that the pressure doesn't kick up?
Why would you want to make it heavier?
So it can sustain the pressure.
Yeah, because you may encounter a zone. Just to back through your logic of your question, because you may encounter a zone that has high geopressure. And that's happened. And that was a unfortunate thing, right? The Gulf of Mexico a few years ago, made a movie about it. I understand they didn't close off the pressures properly enough. Mud weight wasn't high enough. It's actually a different problem, but similar to that, right? So, how do you correct for that? We just have to know. It's all recorded in the log header.
So before,
But keep in mind that the mud is circulating.
yeah,
See it, so it's circulating, so it's kind of integrated.
before they run a log tool, do they circulate all the mud through so that they have a uniform content? Because I feel like
Well,
there's no way of accurately knowing if you change the mix, how long it's going to take for us.
Yeah, the mud is circulating all the time. Well, when you're drilling, right? So as you're drilling, so the mud is coming down through the drill stem, it comes out through the jets and the bit, and comes back up and circulates. So that's kind of homogenizing the mud to some degree. course, it will be recorded when they add more, say, barite, for example, to the mud. That's going to be recorded, so you know something about it. But you have a lot of homogenization that's going on. But yeah, to an engineer wanting to know exactly what it is, yeah, it's a bit frustrating because you started off with a heterogeneous system, but it's become homogenized because of circulation. The other thing you know is temperature, because that doesn't get homogenized, right? Temperature stays the same. You have to correct your temperature. You have a
Yeah, so does barite, like the addition, when you add more barite to the system, does that actually change the resistivity? Or is it just whether it's salt water or fresh water?
Well, it could change it. I mean, barite has a fairly high resistivity itself, but it's going to change things by displacing, and that's what it's supposed to do, by displacing some of the fluid that has a very distinctive resistivity. Okay. So again, that information will be in your log header, or if you're dealing with LAS files, the digital files, it'll be in the file header, or it should be. If it's not, then somebody did something bad, right? Not bad, but they keep all the information. But the point is that your formation resistivity that represents your uninvaded zone. That's what you're interested in. But you have to understand all the others, okay? So that's going to be a function of, to first degree, how much water is present, assuming that your matrix has infinite or near relatively infinite resistivity. Like it's an insulator, okay? Depends on the salinity of the water. The natural waters don't have all the same salinity. That's kind of intuitive. As you drill deeper in the earth, what do you think salinity is going to do? It's probably going to go up, at least in some simple way of thinking. So there's reason to think about variations in resistivity within your borehole system. Most of it's going to come from the fluids that are there to begin with, the original salinity, RW, meaning the resistivity of the formation water, as opposed to the matrix and the water. But the resistivity of your matrix is assumed to be very large. Now, I don't want to get too much into this because you only use this information if you're going to calculate like oil volumes, which we're not actually going to do. We don't have any oil volumes in this particular project. We may have some on others, but this first one, it's the CO2 injection. We're not expecting any oil. I don't know what they would have done if they struck the oil. That would have been embarrassing. Well, the bad news is we completely misinterpreted everything. The good news is we've got 5,000 barrels of oil per day. Hey, do we back? Okay, but that didn't happen. So you've seen this before, right? This is to answer the question, or at least address the question about why you need to have more than one resistivity log, because this represents the profile of resistivity through the rocks next to your borehole. Here's your borehole. We showed this before. Here's your flush zone. Now, if you're dealing with freshwater mud, let's say you're dealing with freshwater mud. It's got no salt, okay? And this is your flush zone. What has happened to your resistivity here? Gone up or down? Gone up because you've replaced salt water, assuming we're not in a reservoir full of oil, okay? Let's say we're something like in our injection zone. So you've shoved out the salt water that has a low resistivity, and you shoved in the fresh water that has a higher resistivity. And then of course, there's always a transition, right? And then you basically get to the uninvaded zone. So we're not so much, for this class right now, we're not so much interested in understanding how this happens, except in a general sense, but we're interested in understanding why we have more than one resistivity log. Now for gamma ray log, you got one, unless you're talking about spectral gamma ray. But usually, you have one log. If you're talking about neutron porosity, we'll get to that later, you have one log. And just go through your different logs. You got one of these, one of these, one of these, right? Sonic log, density log, neutron porosity log, dielectric log. You go through the whole list of them, you got one of each. Now what's the pain about resistivity logs is you got at least three. If you got anything resembling a modern log, you got at least three. Now why would you have three resistivity logs? Well, the answer's here. But help me out. What am I going to say?
You account for that gradient.
You can design logs to look here, and look deeper, and look deeper, and deeper, and deeper, and deeper. I'm going to show you an example. It's got like at least 6 logs, right? You can easily find those that have 9. After a while, it's like, gee, this is like crazy.
When you run these logging tools, are they all in the same string and you make one pass with them typically?
Yes, yes. So we talk about the more than other class, we can do the mechanics. But you may recall I showed you some example of this picture I took of a logging
Just like
tool.
a steel too.
Yeah, it's maybe it's like from here to the wall, and they try to combine as many different tools together. Why do they do that? Because you're going to lower the tool. You've drilled a hole, you're done drilling, you've pulled up the drill pipe, you've pulled up the bit, right? Unless your measurement while drilling, right? And then you lower your logging tool, which is maybe from here to the wall, maybe longer, and then you pull it up. Now you try to do what? You try to get as many measurements on the tool as possible, because it's really expensive to do this. It's like I'm going to take a trip to France twice, 3 times, 10 times. 1 time would be better, get everything I need rather than making several trips, right? So, and this is a lot more expensive than a trip to France, okay? So, yeah, you try to put as many as possible. And you typically, some are related to others. So like a classic example would be you always run neutron and density porosity. We'll talk about that later. Those two will almost always run together. Okay. Or SP and resistivity tools will almost always run together. Yeah, but you try to get as many as possible. Does that answer your question?
Yeah.
Yeah.
Well, I have another question. Do they never interfere with each other? Not necessarily like their signals, but I feel like to get a resistivity measurement farther out, it requires a different time that tool, like a different rate of lowering and raising that tool.
Yeah, they don't all come at the same time. So some tools have to be slower and some are faster. And they've made improvements so that they can be faster. But yeah, there is a rate that's involved. So some tools just take longer because they are trying, like some of the nuclear tools that are trying to measure particles, like say, well, neutrons, for example, that are scattering from deeper in the formation. Well, you get a better accuracy if you're slower, right? So yeah, there is a rate that's involved. And some tools are passive, some are active. Some might interfere with others. The electrode-based tools are just measuring your current. They're electrocuting the formation, so to speak, but they're not inducing any type of current. But we'll get into that, okay? So what I want to talk about right now is just the idea that you have more than one type of a resistivity tool operating at any one time, because you're trying to see within the formation at different lateral depths. That's the important thing to know. So let's just look at an example. This is from Halliburton. Okay, just a real example. It's actually from your textbook, so if you actually went and downloaded the PDFs, this is just, I think it's, if I remember, page 80. I'm not sure why I remember it's page 80. I don't remember all the pages, okay? I'm not a savant. Maybe an idiot, but not a savant, okay? So it's from your textbook. Here's our gamma ray in black. So now you're an expert in gamma ray, right? Here we go. The black is gamma ray. So your knee-jerk reaction is what? This is over here is that's clean. Maybe it's reservoir, depending on your environment. Maybe it's solid glass. Maybe it's solid stainless steel. You really made a big mistake in drilling somehow. Okay. And this is probably what? That's high in potassium. Whoops, so that's maybe a shale. Okay. So this is porosity. We haven't got to that yet. This is what we're interested in. So here's our key down here. Look at the units. Sometimes you look at these curves, it's like, I don't know what those are. They're just wiggles. And maybe some of the names that they use, HO24, it's like, I don't know what that is. It's some trade name, right? From Bob's well logging company. Well, you can always look ohm meters. Well, that must be resistivity, right? And of course, you're expecting that to be here. Again, cooperation among competitors. Your resistivity track is probably going to be on the middle, or at least it's going to be the right of your lithology track, to the right of your depth track. So you get used to knowing where to look. So, what did I say that we have, because we're trying to look at different zones of invasion, you typically have lots and lots of electroresistivity curves. So how many have got here? We got 1, 2, 3, 4, 5, 6 curves, okay? And here's the scale. Now it's what? It's a logarithmic scale, right? So it's going from what? 0.2, there's no 0, obviously, 0.2 to 200 ohm meters. So you know, look at the scale. I was just talking to somebody just earlier today that was trying to make sense of a log, and the first thing I said, and they didn't know, I said, well, look at the scale. And then they answered the question. Okay, so be a bit pedantic about it. Look at the scale. You'll answer a lot of your questions about the log that you otherwise may be misinformed about. So let's just take this one up here. So you said this is a reservoir, maybe? So yeah, I agree, it's a reservoir. But we don't actually have to take my word for it, because now we can look at these, how many? 6 curves. 6 curves, and what do you notice about them? Just develop an intuition. They're all different, right? You got this one. This is the deep one, by the way. 90 means deep, so it's looking deep in the formation, right? So I guess you could say it's 90. It's designed to do that. It's not necessarily doing that, but designed. So 90 inches is what that, okay? And then shallower and shallower, the green is 24, and then the black is the shallowest one, called focus log. Digitally focused log meaning it's looking very shallow, okay? And that actually shows the highest resistivity. So the very first thing to notice, if you look at these curves, you don't know anything about it. You just notice what? What's the difference between this and that? These are all blank. These are all blank. So the 2 different blanks. These are all separated, and these are all, well, down here, sort of superimposed. And that's the first thing you notice. Look for it.
So when they're superimposed, would you say that maybe the rock resistivity matches the mud resistivity? Can make that something.
Maybe. Depends where they're looking. Are any of these logs actually looking in the borehole itself? They're not really meant to. Okay, so let's take this one right here. They're all the same. It's like, well, that's a drag. I've spent money for 1, 2, 3, 4, 5, 6 readings, but I get the same number from each. Maybe I should have got just one, paid for one, since they're $200,000 each. Or buy a house or a car or something, you know, several. But it's actually useful to have all of them. Okay? So what is it telling us here? They're all the same. What are all the same? The 90 inches, the 60, the 40, and go out further. The 90 versus the 60, 40, 30, 24, they're all the same. And then this digitally focused, which is like that much, they're all the same number. What is that number? Well, it is kind of, that's 0.2, what's that? Somebody help me out. That's 0.2, what's that?
2.
Well, it's 1. Okay. 10, 20, etc. up to 200. Okay. So, what is it telling us when they're all the same? Let's go back to this picture. Whoops. So if they're all the same, and one log is looking here, one is looking here, another here, 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 and they're all the same, well, what does it imply about this picture? How do we have to redraw this picture to account for them all being the same? It's all uninvaded. It's all the same color. You have to, like, if I don't have different colors of blue, it's all uninvaded. Or, now if it's all uninvaded, well, how would I redraw this? This is all light blue, right? So that's one possibility. It's all uninvaded. Or it's what? It's all uninvaded, or it's all invaded, right? So maybe you drilled into a pipe, or sewer pipe or something. So like, it's really invaded, okay? So there's no stratification. It's all the same. So it's either all totally deep invaded or not invaded at all. Does that make sense? Now, the most likely possibility, unless you drill into a pipe or something, is that this means it's uninvaded. But it could be deep invasion. Gotta be careful. So what would it mean if you had no invasion? You're probably going to answer that question. What does it imply about the rock type? If there's no invasion, yeah, geologists use the word tight. In Britain, that means you're drunk. Okay, different. Okay, but it means there's no porosity. But it could have porosity, but still look like that. How could it still look like this, all superimposed, and still have porosity?
Impermeable.
It's not permeable. What if I have, what if you drilled into this? Unlikely scenario, but illustrated perhaps. You drilled into a big stainless steel something. You really got it. I mean, they have directional drilling these days, right? You never know where you're going. Maybe you drill into a competitor, maybe you drill into your own well. I don't know. But it's stainless steel, but the steel is for some reason really bad. So it's full of voids that are not connected. Well, if you did that, as unusual as that would be, right? That's what you would get, right? You would get no invasion, even though you might have huge, maybe you got 50% porosity, huge porosity, but they're not connected. So, what's the moral of the story? If you have curves superimposed, that says there's either very deep invasion or more likely, if you're careful, that there's no invasion. And that means there's no water getting through. So that means you just drilled into something not permeable. So the simple thing is that if all the curves are superimposed, it means that you just don't have any permeability, which is a useful thing to know. Does that make sense now? So that is why, well, actually it was worth collecting each one of these curves for $200,000. We'd rather have that than the 3 fancy cars or whatever you can buy for that. Okay. Now, what would you use to back this up? So let's say, okay, we decide this has low permeability. What are rock types that have low permeability? Well, lots. So let's say you're drilling in the Gulf of Mexico, which is where this happens to be. What type of rock type would have low permeability? There's more than one. Low permeability rock type. Gulf of Mexico. Sand, shale, some other stuff in there. So it's probably shale, right? Shale has low permeability, but can have very high porosity, just that the porosity is disordered. It's not connected, it's not cooperating with another. You got a hole here, a hole here, a hole here, they're not connected. Okay, geologists that study sedimentary rocks can talk for hours about why that is. Suffice it to say that shales can have high porosity or good porosity, but they almost always have low permeability. That's why you have to frack shales if you're doing unconventional resource development, right? The stuff is there, but you've got to fracture it in order to get it out, to get it to flow. So that's the whole business of fracking, right? So let's say we decide this is shale. How would you back that up? The answer is always look at another log. Well, we have some other logs. We have these. We actually know about them now. So what is the gamma ray telling us?
High capacity.
Yeah, so right here, gotta be careful. Let's blow this up. Okay. I'm getting really good at this. Are you looking down? I can do this now. So here we go. We have high gamma ray, low deflection, right? Whoops. This must have hurt me. Okay. So high gamma ray, low deflection. All of my electroresistivity curves are superimposed. There's no invasion, suggesting or implying, proving that it's low permeability. Either that or it's deep invasion, but let's say it's low permeability. So this checks out, right? Because a shale would look like this. Now, what if I had this and I had a signature that looked like that? You know what I'm asking? What if my gamma ray signature looked like that between my 2 fingers? And my electrical resistivity looked like that between my 2 fingers. What would you do then? What are your possibilities? See what I just asked? I have this, yeah, it could be deep invasion, like I have like 10 Darcys. Again, you a bunch of pipes, just the water just going fast as you can, right? Well, that's probably not likely. But that's one possibility number 1. What's possibility number 2? For these two to go together.
And like salt or something.
What's that?
In salt.
Salt, right? So salt is clean. It's got no potassium in it. It's just NaCl, right? You might remember that, okay? And of course, it doesn't have any permeability at all. 0. None, nothing, right? So that could be it. What's another possibility? We got salt, halite. We've got very deep invasion and a very good permeable Reservoir. What's another one?
And you got oil.
You have oil, but how would you split? Yeah, if you have this and you have oil, but it doesn't explain the fact that you don't have separation. Because unless you have oil all the way through your horizontal column. So you could get that, but that's not likely, because in this case you're dealing with fresh water, as it turns out, and some of that fresh water would displace the oil, especially if you had good permeability. Okay. What if you just had a quartz sandstone that just had really rotten porosity? It's very well cemented. Now somebody explain cementation. Yeah, can you help us out? We talk about marbles in a jar, but
Yeah, so cement would just be the, I guess, liquefied portion that filling the pore space opposed to fluid or air. So as it compacts, this solution allows for fluid cement in these pore spaces.
if you have everything's being dissolved and redeposited, it's a dynamic system. So something's being dissolved over here and being redeposited somewhere else or recrystallizing, as Jeff said. Okay, that's what holds the grains together, right? Because most rocks, like that one I just passed around, well, it's not just a handful of sand; it's being held together by something. We call that cement, and the most common cement is calcium carbonate. Just so you know. But what if you had cementation just filled in all the pore spaces? So there's none left. So you had something that was clean, right? So it's like, well, it could have been a reservoir, except now all the pore spaces are filled up with cement or calcium carbonate, holding the quartz grains together very nicely. So it's behaving almost like fused quartz again. It's not really fused quartz. It's just quartz that's held together by calcium carbonate, and there's nothing else left. So that could also be this type of signature here. Okay, so maybe spent too much time on this, but I want you to get the idea that the logs in electrical resistivity, the separation of the logs, first tells you is it permeable. So that's the very first thing you can tell, right? And if they're all and if they're not separated, well, you could have very deep invasion, but the most likely thing is that you got no invasion. So that means the rocks are not permeable. That's a very important distinction to make, obviously. Okay, and it's going to help because if you're a stratigrapher, say what is a stratigrapher? Well, a stratigrapher is a person that tries to identify where they're looking in a column of rock. Is this the A sandstone? Is it the B dolomite? Is it the C limestone? Not very clear with names, right? A, B, C, right? Which one of them are you looking at? Maybe the A sandstone typically is permeable, but the B limestone is not. And so it has a typical signature like this versus that. So that's actually what you would use your resistivity logs for in terms of correlation. Assuming that the fluids are the same. Now, if the fluids are different, then you can't use it for correlation, at least not without a lot of caveats. So that's the very first thing, right? It's just invasion versus non-invasion. Now, we actually can use the displacement along the scale to talk about, well, are we looking at oil or gas or water? But we're not going to worry about that right now because this is a CO2 injection site, and we do that in another class. Okay. Any questions about this? Again, we spent a lot of time on this, but it's a very nice example. It's in your textbook. You can stare at it later if you want. By the way, I will make all of these available, and I will send you an email, hopefully tonight, telling you where to get them. Okay, it's over in the geology office. Okay, so well, that's not what I wanted. Okay, so it's about time. I guess it's time to go. So what we'll do next time is finish up on resistivity, just kind of review it. Talk about two different types of resistivity logs because it's a bit more complicated than what I've laid out, and then we'll talk about the third type, porosity logs. And then that's pretty much it for different log types. What we'll do after that, it might be after Bill comes, just so you know, we'll talk about how you connect the logs to your seismic data. Because your logs are in, no, I'm supposed to be quiet. Your logs are in depth, but your seismic data is in time. So how do you eventually get this into your seismic data? that's where we'll end up with. Okay, that's all I have. So thanks very much for coming.
Bill wanted me to make sure you got an email from them, and they emailed him back about going to the conference.
Oh,
Yeah.
Like, so did everyone email him back? If not, do that today. Okay.
yeah, I've been there. It's a very good conference. It's state of the art in this type of work.
Who's that?
Denver, and all expenses are paid. We'll get you guys out there. I mean, it's gonna be